Hello everyone, my name is Kabir Kashyap. In this video, I'll be talking about IR stretching frequency, and I'll be explaining to you what stretching frequency is, how it is seen via a graph, and how do we compare stretching frequency values for different molecules, and what is the relationship between what are the various factors which determine the stretching frequency, and what is the relationship between the bond order, the bond energy, and the stretching frequency, right? So why is stretching frequency studied? Stretching frequency is a really interesting idea or a concept which we can obtain via the IR spectroscopic graph. Now, what is an IR spectroscopic graph? Why do we plot it? Now, certain molecules react differently when IR light, that is infrared light, is passed through it. So when you put that on a machine and let IR light pass through it, you get a graph. And what does that graph contain? It contains various peaks and valleys. So each of the peak corresponds to a particular kind of molecule or particular kind of functional group that is present in the molecule. So that is why it helps us to analyze the molecule and gets to know what kind of functional groups are present in the molecule, right? So how is stretching frequency related to it? Now, first of all, let me explain to you what is stretching frequency. So stretching frequency is different from the usual term of frequency. Now, it is not really something which is per unit time or something. It is basically related to the energy of the bond and the vibrations of the bond, right? So what happens in IR spectroscopic graph, that many peaks show up in that graph of the molecule. So there would be big peaks, major peaks, which correspond to stretching, and minor peaks which correspond to the bending. Now note that this stretching and bending is meant by the bond, that say there are two atoms A and B, that if we have A bond B, then the stretching of the bond is represented by a major peak and bending of the bond is represented by a minor peak, right? So this is the basic idea of stretching frequency, and it is different from the usual meaning of frequency. It relates to the energy of that bond and the energy required to vibrate for the vibration of that bond while it absorbs the infrared light, right? So based on this definition, it can be clearly observed that stretching frequency is actually related to the bond energy and the bond order. That higher the bond energy, you would require more energy to increase the length of the bond, you require more energy to stretch the bond. So it would absorb higher energy of infrared, it would absorb high energy of that infrared light, so it would be harder to stretch. So bond order and bond energy are directly related, and they are directly related to the stretching frequency of the molecule, right? So yeah, and this is also true vice versa, that if you decrease the bond energy, you require lesser energy to stretch the bond, and hence lesser stretching frequency. Alright, so this is the idea behind the stretching frequency. It is basically related to the bond energy and bond length. Now, coming to some ranges and data. Now, on the graph, you will see, if you see a peak around 3000 centimeter inverse, those peaks correspond to CH bonds. So this is an experimental data. And similarly, if you see peaks around 2000 to 1600 centimeter inverse, these peaks correspond to carbonyl groups. Stretching frequency for the carbonyl group, right? So what will be given to you in questions? You will be given certain carbonyl groups attached in certain formats to various metal centers, and then you will be given certain ranges of that. And from those data, you have to find how many terminal group carbonyl groups, how many bridging carbonyl groups, how many bridging mu2 and mu3 carbonyl groups are present. So let me first state the ranges. So for the terminal carbonyl group MCO, the range is between 2120 and 1850 centimeter inverse. Similarly, for the bridging mu2, that is when CO is directly attached to two metal centers, it is 1850 to 1700 centimeter inverse. And for the bridging mu3, it is 1730 to 1620 centimeter inverse. Now, why is this helpful? Now, you may be given any value between these ranges. So, and they might be more than one in number. Say that means, say in a question, you are given three frequency values, 2000, 1990, 1980. So by that data, you can easily guess that okay, these three are the terminal MCO values, and the number of bands do not matter. Like we are giving three bands, it does not matter, only the range matters, that these bands lie in this range of 2120 to 1850 centimeter inverse. That means these correspond to terminal MCO values, stretching frequency values. So yeah, so that is why this range becomes important, and it's important that you learn these values. It helps in exams, right? So like how is stretching frequency actually related. Let me explain to you via this very simple idea. Like if you have an MCO, that is M single bond C triple bond O, here M is single bonded to the C, that means there is lesser back bonding in M and C. Now as resonance happens, if there is electron density over metal atom, so this triple bond will break, this particular triple bond will break, and it will be a double bond, and this metal electron density would come over here, so it will form a double bond. So what that does is reduces the bond order on this atom, on this CO bond, and therefore it reduces the stretching frequency of the CO bond, because I told you stretching frequency directly related to the bond order and the bond energy of the atom, of the molecule, right? So more the electron density on metal center, lesser will be the stretching frequency of the CO molecule. And similarly, higher will be the stretching frequency of the MC bond. Why? Because the electron density, that is the bond order of MC, is increasing because of that back bonding of the lone pair of electrons on M. So this is the reason how you like why this more like why if a metal center has a more electron density, say a negative charge or something, or a lone pair sitting in one of the orbitals, how that affects the CO stretching frequency and also affects the metal carbon stretching frequency, right? Now let me explain to you via certain examples. First example is, say if you have a metal center and you have, say, all these 6 ligands, and you're given 2 ligands, say one is PME3 and second PF3. You have to compare the stretching frequency. So you have to understand that because what is the difference in these two? The difference is between this Me and F. Now what would the ligand attached to metal atom do? It would either try to withdraw electrons from this metal center, right? So if you have to compare the stretching frequency of carbon and molecule, so if the other ligand affects this back bonding to the CO molecule, it would affect the stretching frequency. Now what does Me do? It's an electron donating group, so it would increase the electron density on the metal center and thereby increase the back bonding of CO. That means it reduces the electron density, that means it reduces the bond order of CO, and that's why it decreases the stretching frequency of CO. But in the case of PF3, which is an electron withdrawing group, it reduces electron density of M, thereby increasing the stretching frequency of CO. Similarly in this question, like in this question also, this ligand, if it is a good electron donor, it would increase the electron density on M, thereby decreasing the stretching frequency of CO, and vice versa. Coming to the third question, suppose if CO was bonded to a Lewis acid. Now what does that Lewis acid do? It withdraws electrons from CO. How does it withdraw electrons from CO? That means if you have, say, this system CO, and there is a Lewis acid around, it would require electrons. So oxygen would donate this electrons to the Lewis acid. This would decrease this bond order of CO, because already this is saturated with complete all 3 bonds. So if you are increasing the bond order here, it would decrease the bond order over here, and therefore CO bond order will decrease, and therefore the stretching frequency for CO will also decrease. So therefore the Lewis acid actually decreases the stretching frequency of CO. So yeah, this was the stretching frequency concept. Thanks everybody.